Hi guys, welcome back to the second video of this short playthrough tutorial for Moon. In the last video we saw how to set the game up, what the bits actually represented, and some of the basic manipulation cards. So we're not going to cover those today. We're going to go over the other cards. So first I'm going to start with the bug cards. These get shuffled, there's two of them, they get shuffled and introduced into your goal deck. So let's say this is my first goal and I manipulate some of the registers and I manage to solve it. Yay, discard. Next one. Okay, this is slightly more tricky. Let's say I manipulate this, used all my energy, next round, these move up. And then I manipulate them again, and I've solved it. Discard. Next goal. Okay, maybe this is slightly trickier. Let's say I manipulate it like that. It moves up. Next turn. Maybe I can't solve it again. It moves up. Next turn. I managed to solve it. This is discarded. Next card. It's a bug card. This is going to take up that slot now for the rest of the game. So I have to turn the next one over. I manipulate some of my pieces, end of the round. This is going to skip that space and then everything's going to carry on. Next turn, maybe I turn that one off. Again, this moves up, skips that space and carries on. So this is going to take up one of the slots. If this gets to the 5th position, and again I don't solve it by the end of the round, game over. So these are just going to be permanent annoyances in your coding, making you work faster to solve it. Okay, a couple of the other things we'll cover, pretty simple ones, are the error cards. We've got errors for the operations, and we've got errors for 3 of the registers. These again will get shuffled into your goal cards. I guess you can introduce as many as you want to make the game harder as you wish. Basically, when you pull these, error, registry C, you can flip this over, and that is now unusable. You cannot manipulate registry C. Obviously when this is pulled you'll discard it. So you cannot use that register. Also in the deck you'll put in these OK cards. When you pull one of these from the goal, this will allow you to reset one of these errors. So in this case, I could reset error C, and I can start using that registry again. The other other errors are with your operation cards. So if I pull error roll, I can put that on top and show that I cannot use that operation from now on, again, until I pull a OK card. If I had a couple of errors and I pull an OK card, I'm going to have to decide which one I want to clear. Okay, the other ones we've got are the reset cards. So you've got one for each registry row, and you've got one for columns 2, 4 and 8. Again, you can choose how many of these you want to add into your goal deck. They shuffle in. When you pull one, reset 4. I go into the column 4 and I'll reset them all to 0, just like they are here. So in this case it wouldn't make any difference. But if I pulled registry A, I'd have to flip all these over, back to zeros, and discard the card. Go to the next goal card. So they're just slight annoyances, and to make your game a little bit more interesting and a little bit harder. Okay, so we're going to talk now about these 3 red cards, OR, AND XOR. So these all cost half an energy. So OR copies all of the switched on bits from one registry to another. So I could use this on registry B here, copy into registry A. It's only going to copy the switched on bits. So this first bit here is going to stay on, but these other 2 are going to get copied in. So that can be quite useful. And is kind of the opposite. That copies all of the switched off bits. So if I was going to copy C onto B here, it's only going to copy the switched off bits onto there. And then you've got XOR. This is kind of a mix in between, I guess. Again, half an energy unit. This copies all of the switched on bits from one to another, but if it's already switched on, it turns off. So if I was going to copy C into B, it's going to copy a switched on bit into another. It's going to copy this switched on bit into another, but this switched on bit is already on, so it's going to turn it off. So there's a little bit there to get your mind around. Okay, now we're going to talk about these kind of very pale blue ones. So NOT is probably the easiest to explain. These all cost 1 energy. This is probably the easiest one. This basically just flips every single bit in a register. So if I chose registry B to do NOT, I just work my way along and flip every bit. Oops, there we go. And it's as simple as that. Now these other three, they're slightly more complicated. These are the opposites of the ones we've just talked about. So OR, NOR, AND, NAND, XOR, XNOR, XNOR. Now the easiest way I think to work out how these work is to use the previous examples. So OR, you'll be looking at copying the switched on bits from one register to another. So if I was going to copy C onto B, I'd only be copying the switched on bits. So this would copy, this wouldn't, this wouldn't, this would. NOR is basically just the opposite result. So I think the easiest thing to do is do the OR operation first, which we've done, and then just reverse the result. It's the opposite result. So the same with the other ones. So if we were going to look at AND, or NAND, AND copies the switched off bits from one to another. So if I was going to copy, let me set up a slightly different situation here. There. So if I was going to copy C onto B, I'm only copying the switched off bits. With NAND, again, the result is just the exact opposite. And then, excuse me, and then you've got XOR and XNOR. You do exactly the same thing again. So you're copying the switched on bits from one register to another, but if it's already switched on, it turns off. So again, C and B, I'm going to copy the switched on bits from one to another. So this one to this one, this one to this one, but if it was already switched on, it switches off. And then XNOR is the exact opposite result. That's the easiest way, I think, to explain how they work. It's going to take a little bit of time to get your head around visualizing that before you perform the operations, but I'll certainly make it more challenging. Okay, the last two cards we have to talk about are a little bit easier. They are add and subtract. So we're going to be adding, just like in real life. If I wanted to add, let's say registry C here, we can see is 4 and 2, so this is representing 6. I want to add 6 to registry B, which is representing 2. I want to add 4 plus 2, the result is going to be 6. The result is going to be in the second register that you choose. In this case, I could choose registry B or C. So I can add B to C, and the result will go in here, or I can add C to B, and the result will go in here. So let's add C to B. I'm going to add 4, 5, 6 to 2. The result is going to be 8. So I represent 8, and that's the addition done. Subtraction would just be the exact opposite of that. You take every one from the other, the result goes into the second register. One thing I forgot to mention, these are 1.5 units. So with your energy, you would just have to take one away and the other one you would flip over. Two things to mention with both of these. Adding, it is possible to go to a value that is not able to be represented in the number of bits you've got here. So the total number, if everything is switched on, is going to be 15. 8 and 4 and 2 and 1. So if your number you adds up to more than 15, what you're going to do is work out what that number is and just use the last 4 bits. So it might be useful to have, say, a 16 to represent an imaginary column here. So let's say I wanted to add D to C. So I've got 12 plus 6. So that's 18. So I can't represent that, but I know it's going to be a 1 here, 16, and a 2. So it's going to be 1, 0, 0, 1, 0. I don't represent this 1 because it's not on the board, so I just represent the last 4, 1, 0, 0, 1, 0. So that would be my result in C. The same, well, not the same, slightly different for subtraction. If I wanted to subtract something, let's have an example. Let's say I wanted to subtract 0, 1, 0, 0, so 4. And I want to take away 6. Okay, so I've got 4 in registry B. I want to take away 6, which in registry A. So obviously you can result in a negative number. So what you would do is you go 4 minus 4, which takes us to 0. Just like the cards earlier, you're going to end up then, take away another 1, just like subtract, we're going to end up with an underflow. So that's going to be our minus 1. And then take away a further 1, takes us there. So that's the result of, that's essentially minus 2 from our subtraction. An underflow, and that's the result. And I think that's all the cards done. There's a lot to think about there, a lot of ways to manipulate your bits. Hopefully quite a lot to think about. Enjoy.